Today's topic is statistical terms and notation, and our learning objectives are going to include one, we want to see how much we appreciate variables and data in terms of the meaning and differences, if any. We want to identify the different scales of data and how they are processed in clinical research. And lastly, we should be able to appreciate the use of data scales in clinical research articles. And this is the intelligence cycle. For those of us who have been following this lecture series, this should be familiar. And it shows us how the flow of information in research. We begin with variables, and then from the variables, we obtain data. From the data, we process to get information, and from information, we get intelligence. So our ultimate aim is to get or gain intelligence and deeper understanding of a research problem. But usually we begin by identifying variables that will help us measure that research problem. And we go through this cycle, and then we end up with the needed intelligence. So the first term we are going to look at today is variable. This is a commonly used term, and in different fields, it may have slightly different meaning, but the main use or purpose remains the same. So what is a variable? A variable is any quantity or attribute whose values can change. Anything that the value we assign to it can vary or change from one person to another, from one entity to another, that is a variable. So by definition, almost everything that is in our known reality could fall into that definition of variable, because they can assume different values at different times in different places, okay? So a variable is any quantity or attribute whose value can change. So any attribute, any entity that has that inherent nature to change its value falls into the definition of a variable. So for example, as you see down here, age. Age is a variable because it can change. Sex is a variable because it can assume two forms in humans. Residence is also the same thing. Tribe, all these can change and assume different values for different entities. That is why they are referred to as a variable. And a variable can either be measured or counted. A variable can either be measured or counted. So when do we measure a variable and when do we count a variable? That will lead us to the next phase, which is types of variables. So if you are classifying variable based on data generating process, variable can be classified into two main arms: qualitative variable, which some people call categorical, or quantitative variable, which some people refer to as numerical. Qualitative variables further broken down into nominal and ordinal, and quantitative variable further broken down into discrete and continuous. So let's see if we can appreciate these four types of variables. So what's a nominal variable? A nominal variable is any variable that can be classified into categories whose values, whether measured or counted, can be classified into two or more categories. And within these categories of the variable, there is no intrinsic ordering of values. You can't say one category is higher than the other. A good example is sex. Sex can be classified into male and female. So you can't say that males are better or more than or big. You can't say it is categories of sex, okay? Tribe, the same thing. Within our Nigerian context, tribe can either be Yoruba, Hausa, Igbo, Bini, Esa, Ijaw, you know, different tribes. You can't say there is one tribe has an intrinsic intrinsic might over the other or order. No, these are just tribe. Another good example is yes or no response. So if there are questions that require yes or no response, that is a nominal variable, because you can either say yes or no, and doesn't mean your yes is higher than the no, or no is lower than the yes. So it can just, these are just variables that can be placed into categories. Ordinal, on the other hand, is everything in that nominal stands for, but the difference here is that in ordinal, there is an order, there is an inherent ordering of the categories. A good example is severity of disease. You can say mild, moderate, and severe. What that tells us more or less is that, look, if you are in a category, it confers a degree of rank or ranking. So those who are severe are taken to be more of a bad circumstance than those who are moderate, and so compared to those who are mild. So there's an order. Even though these variables can be placed into categories, the categories that they assume confer an order or a rank. So another example is the level of education. Level of education, primary, secondary, tertiary, is another ordinal variable. So remember, both nominal and ordinal, they form the qualitative variables. So these are variables that can be put into categories. Okay, now discrete. Discrete, on the other hand, is a quantitative variable. And these are variables whose values assume whole numbers. The values can assume whole numbers. For example, episodes of diseases, it can either be 1, 2, 3, 4, and so on. Parity, okay? Parity is another example, para 1, para 2, and so on. So these are variables, they are not necessarily categorized, but they take whole numbers, even though sometimes those whole numbers can be categorized. Continuous variable is the second example of quantitative variable. And these variables can take on any value in the number line, both fractions, decimals, and so on. A good example is age, weight, and even creatinine levels. So these are the different types of variables based on the data generating process. But there's another way we can classify variable, and this is based on how a variable is used in a research process, how the variable is defined in a research. And variable can either be independent variable, popularly referred to as IV, or dependent variable, DV. Now, the dependent variable is also known as the outcome of your study or your research. That which you want to measure, your main interest, that which your research problem or question resolves around, and you really want to measure it. That is the primary outcome or the outcome of your study. That's the dependent variable. But there are things that determine the dependent variable. Those things are referred to as the independent variable. And these independent variables can either be the primary, another name for them is exposures, okay? They are called exposure because upon being exposed to them, they determine the outcome. So we can either have those who are primary exposures, the ones we are primarily interested in the research as a determinant of the outcome, or we have those who we can call the secondary exposures or covariates. These are the ones we call the confounding variables, effect modifiers, or other independent variables that you are not really interested in, but you measure them in your study. So the independent variable determines the dependent variable. And I've already explained them here. The independent variable, okay, they determine the outcome. And these are variables that can be manipulated by the researcher. if you are carrying out an intervention study or an experiment, you can manipulate the independent variable. And like I said, another name for it is the exposure. These are all examples of independent variable, social demographic characteristics, smoking status, or the study arm that you belong to. Like I said, if it is an experimental or intervention study, your study arm is the exposure, and that is the independent variable that will determine the outcome. Then the dependent variable, like I said, is the outcome. So I don't want to go over it again. Good example include the prevalence of diabetes, lung cancer, pain reduction. All these are things that we may be interested in measuring as outcomes in a research process. I've already explained this, but in a diagrammatic way, these are independent variables, the study arm that the study participant belong to divides them into exposed, non-exposed. And that being exposed or not being exposed, that is the independent variable. So you're either in group A, where you take the exposure or the treatment, or group B, where you don't take the exposure or the treatment. Either way, this is the exposure variable here, and this is the independent variable. And they determine the participant's response or their outcome. And that outcome is the dependent variable. So the independent variable influences change in the dependent variable. Independent variable influences change in the dependent variable. And we must really appreciate this, because along the way and going forward, these terms will play a key role in how we kind of explain our research problems and our research idea and conceptualization. We must be able to bring out what the dependent variable is and what are the factors that will influence the dependent variable, which are known as the independent variable. So if we move on now to this example here, this is a journal article, and it is titled Socio-Demographic and Regional Disparities in Utilization of Intermittent Preventive Treatment for Malaria in Pregnancy, Nigeria Demographic Health Survey 2013. Now, just looking at this title for this particular article, you can already spot the dependent variable and the independent variable. If everyone should take a minute to look at this now, you notice that the dependent or outcome variable that these researchers are interested in is utilization. Utilization of intermittent preventive treatments for malaria in pregnancy. That is the outcome or dependent variable in this title. And what are the independent variables? The independent variables here are the social demographic and regional disparities. These are the independent variables that will determine or influence the utilization of intermittent preventive treatment for malaria in pregnancy. So just looking at a title, you should be able to bring out the dependent or outcome variable and the independent or exposure variables. So that is key, and that is very important that we appreciate here. Now, a variable can be random. A variable can be random, and this is the real reason why we carry out research. A variable can be random. Let's look at it. What is a random variable? A random variable is a variable whose values is determined by chance. A random variable is a variable whose values is determined by chance, nothing more, just by chance. So like our date of birth is determined by chance. The last normal menstrual period is determined by chance, when it will come. Age still is dependent on date of birth, which is determined by chance. Our PCV level at any given time is determined by chance. Sources of information, sex, and so on, all these are determined by chance. So any variable whose value, the value it gets, if it's determined by chance, then that variable is called a random variable. Now let's take an example to drive this home very well. These are three persons, 1, 2, 3. they all have the same weight, 70, 70, 70 kg. But let's look at their PCV. You notice that despite having the same weight, their PCV levels are not the same. This is 34, 47, and 40. In a situation where a variable is not determined by chance, where that is called, in some field, is called deterministic system. In a deterministic system, everything is already determined. If you are weighted 70, then you should have a given weight. And everybody that weighs 70 should have that same weight. But how come, despite having the same weight of 70, everybody has a PCV differently, that has different values? Now, this relationship, this variability here, these changes, is our responsibility as a researcher to account for that change. That's why we carry out research. And if we are able to account for that change, it will help us to predict the next person's PCV. Given the weight, we can predict better. So a deeper understanding of the pattern and the variability or randomness in the values of a given variable help us to understand how that variable functions. And by the time we understand how the variable functions, we gain a better control. We can manipulate the relationship, we can manipulate that variable. Same thing, despite having the same weight, the systolic blood pressure measured in millimeters of mercury is different. Why? Why aren't they having this? Why aren't they the same? Why is a weight of 70 kg, same individual, same weight, having different blood pressures? Why? Same thing, even their knowledge of statistics is different. Same individual with the same weight, but having different knowledge of statistics. This guy here knows statistics, but these other ones, they don't know. So all these variabilities, given an independent variable, is what we try to account for in research. And up and until you are able to account for that variability and explain it, you have not done justice to any research effort. So random variable is the essence of research. We try as much as possible to account for that randomness, that variability, given an independent variable. So now let's move a little bit further into data. What is data? Data are observations of random variables made on the element of a population or a sample. Data are the quantities or qualities measured or counted. Remember earlier we did say that variables are either measured or counted. This is it here. If a variable is measured or counted, what you get, that value that you assign to the variable, that numerical value that you assign to the variable, and you put it down and you write it down, and then you now have a collection of values. Those are called data or a data set. So data is a measured or counted variable. If you don't measure a variable, you cannot get data. If you don't count a variable and then you put down your response or whatever you get using numerical values, then you don't get data. So variables and data, they are not the same. They are different. So variables remain a variable until it is measured or until it is counted. Like I always give a very funny example. Height is a variable, but height in centimeters is data because it simply means that you have measured it in centimeter. Because you can as well measure height in different other scales. So the scale that you have used to measure a variable, assign a data type to it. And that is the next level we are moving in, types of data scale. So if you measure the variable and you assign values to them, you can either have the type called categorical or the type called numerical. The categorical data are further broken down into nominal and ordinal. Surprisingly, the nominal and ordinal data still retain the same explanation as the nominal and ordinal variable. But on the numerical arm, the numerical is further broken down into interval and ratio. Interval data and ratio data. And let's see if we can gain a deeper understanding. So the nominal data, like I said, still have the same meaning. These are data that are scaled into categories, and each category, they are all mutually exclusive, which means if you belong to one category, you cannot belong to another category. They are mutually exclusive categories. So when you measure a variable and the values you get, you put them into categories, that is a nominal scaled data. And those categories don't have an inherent order. They are just categories. That is a nominal scaled data. A good example is sex, male, female. We put them into two categories, category 1, category 2. HIV status, yes, no, sorry, this is 0, not 1. Yes is 1, no is 0, sorry about that. So these are nominal data scale. Ordinal data scale, on the other hand, has an ordering. They are just a little step above nominal, like we've said. The individual categories are mutually exclusive. However, each category has an inherent rank to it. So a good example I've given before is severity of disease, mild, moderate, severe. You can give them 1, 2, 3. So which shows a ranking. Okay, and most things we do in medicine, we rank them, mild, moderate, severe, and so on. Big, bigger, biggest, bad, badder, baddest, all those kind of stuff. So all these are examples of ordinal scale data. Then interval scale and ratio scale, these are the numerical scales. Remember, we are talking about data. If we are talking about variables, we'll be talking about discrete and continuous. But in this case, we're talking about interval and ratio scale. So what's an interval scale data? Interval scale data, these are data that allows for degree of difference between variables. It has an arbitrary 0. It allows for a degree of difference. Remember, in the nominal and ordinal scale, there is really no degree of difference. You know that, yes, severe is higher than moderate. Moderate is higher than mild, we know. But by how much are they higher? We don't know. What is the difference between mild and moderate? What is the difference between moderate and severe? We really don't know. We really don't know. So, and different scales like that we use in medicine, we put variables, we measure them and put them into categories. We do it, but sometimes we don't really know the degree or the amount of difference between one category and the other. But interval scale takes it a little bit further to tell you the degree of difference or the amount of difference between two categories. So a good example of interval scale is the Celsius scale. When we talk about, that's degree Celsius, when we talk about temperature. Okay, you notice that in the temperature scale, we have a 0 degree Celsius. That 0 degree Celsius does not mean the absence of temperature or the absence of heat. No, doesn't mean that. No, it does not. That 0 degree Celsius is just there so that we can be able to measure intervals between temperatures. So if you have 0 degree Celsius and you move to plus 30 degrees Celsius, that's an interval of 30. What if you move back to minus 30 degrees Celsius? It is also an interval of 30, equal interval. However, you cannot say that plus 30 is twice as hot as minus 30. You can't say. So there is no multiplication here. It's just interval, difference from one point to another. That's interval scale, difference from one point to another. And usually it has a fake 0. That 0, you can say 0 degrees Celsius But indeed, that 0 degree there does not mean the absence of that variable. It does not mean the absence. It's just for difference, for us to get intervals. Another example is, let's say, date of birth. Let's look at this date of birth. Okay. So what is the fake 0 with respect to the dates of our births or dates generally? The fake 0 here is usually around the birth of Christ. Before the birth of Christ, if you follow how time is dated, you realize that, let's assume the days of the dinosaurs is 65 million years. As we come towards the birth of Christ, the dates shrink towards 0. The birth of, let's say, Adam and Eve is 4,000 years. The birth of, let's say, Abraham is 3,000. You notice it's shrinking towards 0, because 0 is the focus point for us to get intervals. And by the time you start getting to David and all that, we are shrinking more towards 0. And as soon as the common era or the birth of, around the birth of Christ, we hit a point called 0 point, and then we start advancing again until you get to your own date of birth. It's advanced and keep on advancing. You get to 1900, the year 2000. Now we are in the year 2020 to keep on advancing. And that is how dates operate. So that is the interesting part in interval. The 0 is there, but does not mean the absence of people being born or the absence of date or age or individuals. It's just a point for us to get intervals. On the other hand, ratio scale has a true 0 point between intervals or between categories. It has a true 0 point. In other words, if you say 0, it truly means the absence of that variable. If you say age, that this person is 0 years old, it simply means this person is not born yet. It's the absence of that variable. And we use a lot of ratio scale in clinical medicine, where the absence of a given assay or given variable simply means the absence of it. So if we assay for selenium and you have 0, it means there is no selenium. So 0 is truly 0, and ratio scale is the ultimate scale that embodies all the properties of interval, ordinal, and nominal scale. Now, if you take it a little bit further, nominal scale, you can count them, and we usually present them as frequency, percentages, or mode. Use the mode to represent them. Ordinal, same thing, we count, and we represent them using frequency, percentages, and mode. Interval scale, we can only add or subtract interval scale, nothing more. We can only add or subtract. So your date of birth can be added or subtracted. That is why we actually subtract the last normal menstrual period from the current date so that we can estimate the gestational age of a fetus. Those are dates, so you can subtract dates, okay? And you can add dates. You can do all that, but you cannot multiply dates. You cannot divide dates. That is the limitation of interval scale. And we present them as frequencies or percentage. If we decide to categorize interval scale, we can take interval or ratio scale, we can categorize them into nominal or ordinal scale. We can do that in research. So if we recategorize or if we categorize interval scale, then we present them as either frequency or percentages, just like nominal and ordinal. But if we leave them as the numerical values, then we can present them using mode, the median if normally the mean if normally distributed, or the median if skewed. Same thing for ratio scale. However, the good thing about ratio scale is that we can perform addition, subtraction, we can divide, we can multiply, we can perform the whole board mass on ratio scale. So that is why we can, with respect to age, we can subtract our age, we can divide my age with your age, we can multiply my age with your age, we can do anything with age. We can do same with PCV, we can do same with weights, heights, we can do all that because they are ratio scaled data. And we can perform all these operations on them too. Now, let's move on a little bit to population. How do we define population in statistics and in the research environment? All members of a defined group about which the researcher wishes to draw conclusion is a population. Now, there are key terms here: members and defined group. Defined group. You must define the group to warrant that title of a population. All members of that defined group which the researcher wishes to draw conclusion on, that forms a population. So we use this term a lot: population of this, study population, target population, reference population. What do they mean? What is the difference? So a target population or a reference population is sometimes, or in some cases, people will say a study base. This is the population that we want to generalize our findings from a research onto. So if you are interested in looking at diabetic retinopathy among diabetics seen in our clinic, our main interest is not just those seen in our clinics. Our main interest is diabetics generally in that defined population of or community. That's what we are interested in. However, most often we don't get access to that target population because they are too large. In fact, your target population can be the whole world. If your findings is to be generalized to the whole world, it can be a country, it can be a state, it can be a local government, a council, or it can just be a simple community, or it can be a group of patients in your hospital that you see. So you must be able to define your target population or the population you want to reference your findings onto. Then, because we cannot have access to the target or reference population, usually we now look for a study or source population. There's a lot of terminological differences here. So some people can switch all these terms, but you must be able to explain what your term means and try as much as possible to use the right term. So a source population or a study population is the accessible population. This is the population that you can gain access to. So I think I gave an example in the next slide. We'll all see it together. Then the sample is those people that finally make it into your study, the study participants. So we must understand the difference. Now, your sampling frame comes from your source population. These are the people that you have access to. So you give each of them a number and put them in a sampling frame. And that sampling frame is where you pick your sample from. So that is the source or study population. This is an example to further explain. Now you can see target population, source or study population is embedded in the target population, and then the sample is embedded in the source or study population. So the idea is that your sample must be representative of the source population, and the source population must be representative of the target population. I must stress here, there are some authorities who will say that the source population is actually the target population, and the target population is the source population. That's just a difference in terminology, but please understand and be able to explain the term that you are using at any given time. So this is a good example. Let's take a look at this example. A study of children with a mental disability in the age of 6 to 12 years old with an IQ between 50 and 70, and you select 30 people from this group for interviews. Now, what is the target population? This target population is children with mental disability. Children with mental disability. And surely you cannot have access to all of them. So what is your study or source population? 6 to 12 years old with an IQ between 50 and 70. This you may be able to get access to. And then when you pick from this, you get your sample. And in this case, they pick 30 children. So this is an example of how you relate target, study, and sample population. Now, what is a parameter? A parameter describes a population. A parameter is used to describe a population. If you are able to have access to the source or the target population, if you are able to have access to it, and you measure a given variable, and you get your data, and you look for the mean of that data. That mean is a parameter because that mean is generated from a population, not a sample of that population. That's the difference. So if you get the total population, you have access to it, and you are able to summarize and characterize that population. And you characterize them with a given value. That value that you have used to characterize or summarize data generated from a population is referred to as a parameter. So when you hear the word parameter, parameter is trying to describe a population. And these parameters, they are represented by lowercase Greek alphabets. Lowercase Greek alphabets. They are used to describe parameter of a population. And these are all the Greek alphabets. These first ones here are the upper cases, while the next ones are the lower cases. So this is popularly known as alpha. I know we know this. This is beta, gamma, delta, epsilon, and so on. So the common things that we know in statistics, I'm sure many of you are aware of mu. Mu, the uppercase for mu is this capital M, but the lowercase is mu. So we use these lower cases. We don't use the uppercase. We use the lower cases when we are trying to describe parameters of a population. So anytime you see the use of mu or alpha or beta, we are talking about population, not the sample, never the sample. Please take note, because you will see, even when you are calculating your sample size, you will see Z alpha, Z beta. That tells you that whatever it is referring to is to the population, And I'm sure we're also aware of pi. This is pi here. Pi is used to represent population proportion. And this is the very popular sigma. And if you notice, there's another sigma here. This sigma that looks like E is a summation sign. It's a summation sign. Okay, it does not reflect any parameter of a population because it's an uppercase Greek letter. So we are interested in the lower case here, which is this sigma, which represents population variance or population standard deviation, sorry. If it is squared, it becomes population variance. Okay, so all this, if you notice down here, you notice another one here, the chi. We are very conversant with the chi. That's the lowercase chi. So that's why when you are writing your chi-squared test and you want to represent it, this is the symbol here, not X, the way we usually do. But you see there's a slight difference in the way the lines go. It's as if it's curved. So this is chi. So all this is the way we represent parameters of a population, lowercase Greek alphabets, okay? And all what I've been saying is represented here. This is the sigma, population standard deviation, sigma squared, population variance, capital N represent population size, pi or capital P represent population proportion. This is mu representing population mean. Let's look at sample. A sample is a representative group drawn from the population. A representative group drawn from the population. And that could be the study or the source population. Now, you should be familiar with what samples are, okay? We've said this over and over again. It's a subset of a population. Now, we use lowercase Latin or Roman alphabets to denote statistics gotten from a sample. You notice that parameters describes a population. Statistics, on the other hand, describes a sample. We've said it earlier in our lectures. Statistics describe a sample. Parameters describe a population. Parameters are represented by lowercase Greek alphabets, while statistics are represented by lowercase Latin or Roman alphabets. So the very familiar alphabets that we know are Latin or Roman. These are the very familiar, the A, B, C, D. So, but we are interested in the lower case. So we use the lower case here to represent statistics. That is why you see that we use small s to represent sample standard deviation. And if you square it, it becomes sample variance. And these are the symbols here. small n for sample size, small s, lowercase s for sample standard deviation. Square that s, you get sample variance. Bar x, sample mean. And of course, p with a hat on it, p hat representing sample proportion. So you see that the lowercase Latin or Roman alphabet represents statistics for a sample. Statistics describes a sample, parameter describes a population. So this is where we are going to call it a day for today. This is very brief and very straight to the point because they are going to form the basis for us to really understand the subsequent lectures. So please familiarize yourself with these statistical terms and notation. They are key to understanding statistics in medical research. So once again, I want to say thank you to everyone for listening, and always remember that science and statistics are the basis for critical thinking.